Welcome to the deep dive. We are diving into a topic today that is really the foundational icon of the modern world. It's the image that stands in for the entire concept of economic progress, the steam engine.
It absolutely is. It's the unquestioned hero of the Industrial Revolution.
Mm.
If you were to ask anyone to point to a single machine that, ushered in sustained economic growth and this kind of exponential change, that machine, that iron beast of fire and water, it's universally dubbed the prime mover.
Right. And when we trace the timeline of these massive social shifts, like the
Uh,
sudden, really dramatic growth of cities, the steam engine is almost always credited as the catalyst.
Mhm.
It let manufacturers stop relying on the highly erratic power of wind and water.
Or the sheer muscle power of animals and humans.
Yeah.
It truly enabled that transition from what we call an organic economy, which is constrained by, renewable biological cycles, to a mineral-based economy, which is capable of almost limitless scale.
But our mission today is to challenge that popular narrative a little bit.
Right.
We are taking a stack of sources. We've got historical papers, deep engineering timelines, and some really surprising quantitative economic data.
And that data is specifically drawn from U.S. Census records between 1850 and 1880. We're going to use it to see if the common story actually holds up. Was the steam engine's adoption the single biggest catalyst for urban growth?
Or was it something, I don't know, far more subtle, a change in organizational structure that steam just facilitated?
Exactly.
Okay, let's unpack this. For you, the listener, we are tracing this long, surprising history of steam power. We're going from its ancient, almost philosophical origins right up to the modern power plant, and we're trying to identify where the real turning points actually happened. What if the truly world-changing innovation wasn't the hardware, the engine itself?
But the organizational software it was running?
That's the question. So where do we start? Not in 18th century Britain, I take it.
Not at all. Let's start by humbling ourselves a bit. The principle of steam power is not some revolutionary 18th century invention. The idea has been dormant, really just waiting for the right economic and material conditions for over 1,600 years before the Industrial Revolution even began.
That really puts the timeline into perspective. So we have to go all the way back to the 1st century BC, to the famous mathematician, physicist, and engineer, Hero of Alexandria.
Hero of Alexandria, yeah. He ran the higher technical school there, and he's credited with the invention of the eolipile.
The eolipile. It's fascinating. It's the first known steam-propelled mechanism, right? Named after Aeolus, the Greek god of wind.
That's the one. And it was incredibly simple, but at the same time really elegant. It demonstrated these fundamental physics that wouldn't be industrially applied for millennia.
I remember seeing a diagram of it. The basic mechanism is steam is generated in a sealed cauldron. It travels up through some pipes into a hollow metal sphere.
Which is mounted on a pivot.
Right, on a pivot. And then it escapes through these two small opposing bent tubes. And the reaction force of the steam escaping makes the ball spin.
It's essentially the principle of a rudimentary reaction turbine, or even a jet engine.
A beautiful proof of concept. It illustrates the third law of motion, action, and reaction, and it shows that heat energy could be converted into continuous rotational motion.
And yet, it didn't change the world. And that failure to launch is incredibly informative about the nature of how technology actually spreads.
So that's the big question. Why didn't the eolipile lead to an industrial age in classical antiquity? If they had the blueprint, why didn't Rome or Alexandria just run with it?
There are two major constraining factors. You've got the socioeconomic context and you've got material science.
Okay, let's take the socioeconomic one first.
Well, Hero's device, as he details it in his book Pneumatics, was really treated as a novelty. It was a temple wonder or an academic teaching tool. They used it to perform little tricks in temples, like opening doors automatically or making statues move to impress people.
So a parlor trick, not a prime mover. They lacked a demand for a mechanized society.
Crucially, yes. The Roman and Alexandrian economies were built on abundant slave labor. Why would you invest massive resources, intellectual capital, and expensive materials into solving a problem like moving heavy objects or grinding grain when you had limitless, cheap, and easily managed muscle power right there?
The economic incentive for non-animal power was just absent.
Completely absent.
Yeah.
If the opportunity cost of human labor is virtually zero, the cost of developing a new, complex energy technology is just prohibitive. You're not going to do it.
Okay, and the second constraint was material science.
Exactly. To do any kind of practical industrial work, a steam engine needs high pressure. The pressure vessels, the boilers and cylinders of the 1st century BC, were made mostly of bronze or copper. And they had really rudimentary soldering and joining techniques.
They just couldn't handle the pressure.
They couldn't. They would have simply ruptured. Any attempt to pressurize them to a useful degree would have resulted in an immediate catastrophic explosion.
So the idea just goes dormant. It's sitting there, lingering in these obscure Hellenistic texts until the intellectual revival of the Renaissance.
Right. The thread picks up again around the 16th and 17th centuries. This coincides with a new intellectual interest in hydraulics, mechanics, and critically, a growing need for better mining technology.
So we start seeing renewed curiosity, but it's still mostly novelty at this point.
Mostly. Taqi al-Din in Ottoman Egypt in 1551, who described a primitive steam turbine, but it was just designed to rotate a roasting spit. Then Giovanni Branca in Italy in 1629 proposed a stamp mill powered by a jet of steam turning a wheel. Still basically Hero's reaction principle.
And this brings us to that famous, and I think you said highly debatable historical anecdote about Blasco de Garay.
Ah, yes, the Spanish Naval Archives story from 1543. It's alleged that Captain Blasco de Garay demonstrated a steam-powered ship in the harbor of Barcelona, right in front of Emperor Charles V. The report claimed he used a copper boiler to turn some side wheels.
But the documentation is fuzzy.
Very fuzzy. Some reports claim it was a huge success, others say it barely moved. And the historical consensus now leans toward it being either exaggerated or maybe it even used a non-steam, manually powered system.
But the very existence of the anecdote, true or not, it suggests the idea was in the air, doesn't it? The pursuit of steam wasn't just an academic novelty anymore.
Absolutely. It shows that the concept was in the intellectual atmosphere. But ultimately, for more than a millennium, steam power remained a ghost, an idea that existed in this theoretical realm, just waiting for a crisis to make it necessary.
And that crisis, when it finally arrived, was water.
Precisely. The transition from a philosophical curiosity to a practical machine required a dire, urgent problem to solve. And by the 17th century in Britain, mining was the cornerstone of the economy. Coal, tin, copper.
And as miners dug deeper and deeper for these essential resources, the constant catastrophic influx of water seepage became the limiting factor for production.
Exactly. Horse whims and these rudimentary pumps, they just couldn't keep up. The deeper the mine, the more water infiltrated and the more dangerous and unprofitable the whole operation became. They needed a source of power that was continuous, relentless, and could operate far below ground level.
So that need becomes the crucible for practical steam development.
It does. And before we get to the famous engineers like Savery and Newcomen, we have to acknowledge the foundation laid by a French Huguenot physicist, Denis Papin, who was actually working on completely unrelated problems.
Papin, right. A fascinating figure. He fled religious persecution to England and Germany, worked with people like Christian Huygens on air pumps, but his most critical work for steam came from experiments in food preservation.
That's right. In 1679, Papin invented the steam digester. This was essentially a high-pressure vessel designed to soften animal bones to extract fat for dietary use. It was a precursor to the modern pressure cooker.
And he was dealing with incredibly high internal pressures.
So high that his experiments often ended in loud, terrifying explosions.
And out of those failures came one of the most critical safety mechanisms that would ever be attached to a boiler.
The safety valve. It's that simple. To prevent his digester from constantly blowing up, Papin equipped it with a device to automatically release excess pressure. This invention was absolutely essential. Without the safety valve, the Industrial Revolution would have been infinitely more dangerous.
But beyond safety, Papin also made this crucial conceptual leap about the engine mechanism itself, didn't he? Which he published in 1690.
He did. He realized that using steam to force a piston up with massive internal pressure was complex and risky. But instead, you could use steam to fill a cylinder and then suddenly condense that steam using cold water.
And that condensation creates a vacuum.
A powerful, instantaneous vacuum inside the cylinder. And then the immense pressure of the external atmosphere pushes the piston down, doing the actual work.
So the engine isn't being driven by steam pushing out, but by the air pushing in. That seems so counterintuitive.
That's the genius of it. The atmosphere is doing the work. You're just using steam as the medium to create the vacuum. And that atmospheric pressure principle was the basis for the first widely commercialized steam device, Thomas Savery's patent of 1698. He called it the miner's friend.
Savery's device was a direct-acting pump, though, right? No pistons or cylinders. It used steam pressure operating directly on the surface of the water.
Right. It was innovative, but his pump had severe technical limitations. It operated at dangerously high pressure to get the necessary lift, often 8 to 10 times stronger than air pressure. This continually stressed the joints and boilers.
leading to a frequent risk of catastrophic rupture.
A huge risk. And the other limitation was lift height. Because of the physics involved, the pump could only lift water a total of about 55 feet, about 25 feet with the vacuum and another 30 with the pressure.
Which means the boiler and the entire machine had to be located deep underground, close to the water source. That sounds like a maintenance nightmare.
It was a massive problem, especially in dark, damp, cramped mine shafts. It had some regional success, but it couldn't solve the crisis of the really deep, complex mines.
And that's where Thomas Newcomen comes in. He's collaborating with a plumber, John Calley, trying to solve this problem of lifting water from depths of over 300 feet.
And Newcomen takes Papin's piston concept and engineers a solution that was massive in scale, but far, far safer. His engine, which appears around 1712, was purely atmospheric. It used low-pressure steam, generated in a separate boiler, simply to raise the piston to the top of the cylinder.
The power stroke came next. A jet of cold water was injected directly into the cylinder, condensing the steam.
And creating that massive partial vacuum. Then, the 15 pounds per square inch of the atmosphere outside drove the piston down. That was the working stroke.
So it was much safer because it avoided Savery's risky high pressures.
Exactly. Newcomen's engine was a huge success for mine drainage. The first one performed about 5.5 horsepower. It could drain mines far deeper than 300 feet, and it remained the industry standard for 50 years.
But history records that Newcomen was immediately forced into a partnership with Savery. How did that happen?
It's a fantastic early example of patent law shaping technology. Savery's 1698 patent was so broadly worded that it basically covered any device that raised water by the force of fire. Newcomen's engine, though it was technologically distinct and far superior, was deemed to infringe on this broad patent.
So he was forced into a joint venture.
He had no choice. But despite its huge effectiveness in solving the mining crisis, Newcomen's design had this fundamental critical flaw that made it uneconomical for wider application. It was a thermodynamic nightmare.
And that flaw was the heating and cooling cycle.
Yes. To get that condensation and vacuum, the engine had to alternately heat this massive iron cylinder with steam and then cool it right back down with a jet of cold water with every single stroke.
So in every cycle, you're just throwing away the energy you just put in.
Exactly. When the fresh, hot steam rushed in, a huge amount of his energy was wasted just reheating the cylinder walls that had just been cooled down. Massive amounts of latent heat were just lost to the atmosphere,
Which means the engine required gigantic amounts of coal to operate.
making it only economical where coal was literally cheap and readily available, right next to the coal mine. It was a power-hungry regional solution.
Here's where it gets really interesting, because you have this machine that solved the biggest industrial problem of the early 18th century, but it's shackled by its own inefficiency. And it takes James Watt repairing a small model of a Newcomen engine at the University of Glasgow to see this fundamental waste in 1763.
Right. Watt was an instrument maker, not primarily an engineer, and his genius was in recognizing this thermodynamic truth. He calculated that nearly 3/4 of the steam admitted into the cylinder was wasted just reheating the metal walls. He realized that for maximum efficiency, the cylinder must stay hot all the time.
While the condensation process must be isolated to stay cold,
And his solution, the core innovation patented in 1765, was the separate condenser.
such a simple yet profound conceptual leap.
It was. By creating a separate vessel, a tank, that was perpetually kept cold and under a vacuum just for the condensation, the main working cylinder could remain hot at all times. He completely solved the heating and cooling dilemma that had plagued Newcomen's design for half a century.
The result must have been staggering. How much more efficient was Watt's design?
It was a quantum leap. Watt's early engines, commercialized around 1776, used 2/3 less coal to do the same amount of work. We measure this in terms of duty, the foot-pounds of work delivered per bushel of coal burned. Watt achieved a threefold increase in duty.
A threefold efficiency improvement fundamentally changes the economics of the whole thing.
It transforms the engine from a power source that's only viable next to a cheap coal pit into a universal power source that can be affordably used almost anywhere. Before Watt, steam power was expensive and regional. After Watt, it was relatively cheap and globally viable.
But initially, Watt's engine, just like Newcomen's, it only provided linear motion up and down pumping. It was still limited to draining mines, just far more efficiently. The real change came through his collaboration with
Matthew Boulton. Watt was the technical genius. Boulton was the visionary businessman. He provided the funding, protection from patent pirates, and most importantly, the commercial vision to apply this engine far beyond the mines. He challenged Watt to apply it to other industrial needs, like driving machinery, which requires continuous circular movement.
And that necessity drove the invention of the famous sun and planet gear in 1781.
It did. Watt used this specific gear arrangement to convert the engine's linear reciprocating motion into continuous rotary motion. And that conversion was undeniably a key moment in the Industrial Revolution.
Because it meant a factory no longer needed to be located next to a fast-moving stream for power.
Exactly. Water wheels were so unreliable they froze in winter, they slowed down in summer droughts. Steam engines provided power on demand, 204/7.
Which means manufacturers could now locate their factories near markets, near transportation hubs, or, crucially, where the labor force lived. This is the first link in the chain connecting steam technology to urbanization.
And Watt even had to invent a new way to market this flexibility. He was selling one of his early rotary engines to a London brewer who needed to replace the 6 horses that turned his mill.
The brewer wasn't buying coal, he was buying muscle replacement.
So Watt had to devise a measurable unit to quantify his engine's work compared to the existing power source.
And that's where we get horsepower.
The concept of horsepower. It was a marketing pivot, born of necessity, to give non-coal-using customers a unit they could understand. It's remarkable that the unit we still use for our cars has its roots in James Watt trying to convince a London brewer his engine was better than 6 real horses.
That whole suite of innovations, the separate condenser, the sun and planet gear, the concept of horsepower, it transformed the engine from a regional pump into the universal standard for industrial power.
Yet, even after Watt, the engine was largely stationary. Watt himself was deeply reluctant to embrace high-pressure steam. He was worried about safety, he'd seen explosions, and this created a real obstacle for mobile application.
An obstacle that was cleared by Richard Trevithick at the turn of the 19th century.
Trevithick realized that by using higher steam pressures, completely contrary to Watt's low-pressure preference, you could make the engine far more powerful and, critically, far smaller and lighter.
High pressure provided the power-to-weight ratio you need for mobility.
And Trevithick debuted the first rail locomotive in 1804 at the Penydarren Iron Works in Wales. It was a technical success. It hauled 10 tons of iron and 70 men.
But as you mentioned earlier with the eelopile, technology often clashes with the existing infrastructure.
It absolutely did. The locomotive was too heavy. The tramways of the day used these brittle cast iron rails designed for horse-drawn wagons. They just kept breaking under the weight of Trevithick's powerful engine. It proved that while high-pressure steam enabled mobility, the railway technology itself hadn't caught up.
It took another 25 years for the rails and the engine design to really converge into the definitive template for the railway age. And that happened at the 1829 Rainhill trials.
Right. The Liverpool and Manchester Railway held this competition to decide once and for all how they would power the new line. The rules were rigorous, demanding speed, reliability, low weight. They were essentially creating the technical spec for the future of rail travel.
The winner, of course, was Robert Stephenson's rocket.
Designed by Robert with input from his father George and, crucially, from a man named Henry Booth. And Rocket wasn't just a successful engine, it was the birth of a global standard. It hit speeds of 30 miles per hour. It set the 022 wheel arrangement for the next century.
But its victory wasn't due to a single invention, was it? It was the brilliant integration of 3 key engineering innovations that had been developing separately.
That's the key. It was the combination.
Okay, let's break that down. First, the multi-tubular boiler.
Previous locomotive boilers often had just a single large flue running through the water tank. That severely limited the surface area for heat transfer. Rocket, based on Booth's suggestion, used 25 small copper tubes running from the firebox to the chimney, all immersed in water.
Drastically increasing the surface area.
Which meant faster, much more efficient steam generation. More steam generated faster means more power.
But that alone wasn't enough. The second critical innovation was the blast pipe.
The glass pipe is the definition of an elegant, self-regulating feedback loop. It directed the exhaust steam from the cylinders up the chimney.
Instead of just venting it into the air.
Right. And that jet of exhaust steam created a vacuum in the chimney, a powerful draft, which pulled vast amounts of air through the firebox. This made the fire burn much, much hotter.
So the faster the engine runs, the harder it works, the more exhaust steam it produces.
The stronger the blast pipe's draft becomes, which makes the fire hotter, which generates more steam, which makes the engine run even faster. It's a spectacular instance of a machine improving its own performance dynamically.
A thermodynamic miracle. And the third innovation was the direct drive.
The cylinders were angled, later almost horizontal, connecting directly to the driving wheels. This solved the mechanical instability and that uneven sway that plagued earlier vertical cylinder designs, making high-speed operation smooth and reliable.
Now, this focus on rails often overshadows the other potential application for mobile steam roads. There were serious attempts to put steam coaches on British roads in the 1830s.
Oh yeah, they were technically quite successful. Steam coaches could transport passengers reliably, some could hit 24 miles per hour. They were the true precursors to the automobile. But their development in Britain was actively and politically suppressed.
And the primary instrument of that suppression was the notorious Red Flag Act of 1865.
A masterclass in lobbying against innovation. It was pushed by interests tied to traditional horse coach owners and the railway companies, who saw the steam road vehicle as a threat. The act limited them to 4 miles per hour in the country and 2 miles per hour in towns.
And the requirement that just doomed it.
A man carrying a red flag had to walk 60 yards ahead of the vehicle to warn pedestrians and horses.
It made steam travel slower than walking. It just killed the commercial viability of the whole thing.
Completely. And that single piece of protectionist legislation had these massive, long-term strategic implications. It basically ensured that Britain, the birthplace of the Industrial Revolution, focused almost entirely on rail transport, while continental Europe and later the US were free to develop the internal combustion automobile.
Okay, we've established the technical trajectory. From ancient novelty to the Newcomen pump to Watt's efficiency revolution, and finally to the Stephenson's mobile rail template. Now we pivot to the economic data to really challenge this idea that the steam engine was the primary catalyst for the growth of cities.
Right. The traditional hypothesis is incredibly persuasive. Historians like Traustenberg and Rosenberg argue that steam power provided the locational freedom necessary for firms to unchain themselves from rural water power sites and agglomerate in cities near labor pools and markets.
It should be the definitive catalyst for massive urbanization. And we are looking at this quantitative study by Sukhu Kim, drawing on firm-level data from U.S. censuses between 1850 and 1880. This is the exact period when steam adoption surged and the share of the U.S. population living in urban areas doubled.
The data lets us use econometric tools like regression analysis to determine which factors, power source, firm size, labor characteristics, were most predictive of a firm locating in an urban area during this critical 30-year window.
So let's start with the comparison that seems to support the traditional story. Steam versus water power.
When you compare firms strictly on their power source, the analysis does confirm the premise of locational freedom. Steam-powered employees were, on average, 5.5 times more likely to locate in cities between 1850 and 1880 than water-powered employees.
5.5 times. That's a powerful indicator. That seems to validate the catalyst theory completely.
It does, until you introduce the omitted category into the comparison, which is non-inanimate power, predominantly hand power used in small artisanal shops. When you look at the full spectrum, the findings get genuinely surprising.
What happens when steam power is compared to hand power?
The data shows that steam-powered employees were, on average, 0.55 times less likely to locate in cities compared to employees using hand power.
Wait, let me get this straight. If you took a hand-powered operation and upgraded it to a steam engine, the firm was statistically less likely to be in a city.
Yes.
That contradicts the entire narrative that steam pulled industry into cities.
It creates a major statistical puzzle.
Yeah.
The interpretation is that the instantaneous net effect of the steam engine's adoption by itself on urbanization was negligible, and in some cases even negative. Just switching the power source doesn't automatically mean the firm moves to the city.
So if the technology itself wasn't the biggest driver, what variable in the data was most strongly correlated with urbanization?
The data points clearly to the organizational structure of the firm. The shift from small artisanal shops to factory organization was the single most important contributor to urbanization in the second half of the 19th century.
And how is factory organization quantified in this model?
In this specific study, it's defined as firms employing more than 15 laborers. And what the analysis revealed was striking. Regardless of the power source, whether the firm used steam, water, or even hand power employees in these large factory settings, were 2 to 3 times more likely to locate in cities than their non-factory counterparts.
That dramatically shifts the focus. It suggests that the technological necessity of steam power was secondary to the organizational necessity of centralizing large numbers of workers in one place.
Exactly. When the economic model calculated the impact of these changes over time, the shift toward factory production is estimated to have increased urbanization by about 27% at any given point in time.
27%.
Now compare that back to the steam engine. The shift from hand or water to steam power contributed only an estimated 8 to 10% increase in the rate of urbanization over that whole 30-year period.
The factory system was 3 times more predictive of city growth than the steam engine itself. So the steam engine was the tool that made the large factory possible by providing scale.
But the factory, the organizational structure, was the true engine of city growth. And this aligns powerfully with modern theories of urban economics, specifically those based on labor market transaction costs.
Meaning?
When you have large factories that need a diverse, specialized, large pool of workers, and those workers need jobs, the serms and the laborers have a massive incentive to agglomerate, to cluster together. Why? Because labor search and matching costs go down dramatically with density. It's just easier to find the right worker and for the worker to find the right job in a city.
The factory system required a large, predictable, and specialized workforce to justify the capital investment, and locating that factory near the largest available labor pool of the city was an organizational imperative.
Regardless of the power source, the data further supports this when you look at labor characteristics. The study found a very strong correlation between the composition of the labor force and urban location. For instance, employees in firms with a higher intensity of female labor were up to 9.6 times more likely to locate in urban areas by 1880.
That's a huge odds ratio. Why that strong connection?
It's a proxy for the type of industry. Industries that historically relied heavily on female labor like apparel, boot and shoe manufacturing, printing, these were labor-intensive, not raw material-intensive. They benefited greatly from being close to markets and skilled urban populations, so they clustered in cities.
And conversely, resource-intensive industries like flour mills or lumber, they were less likely to be urban.
Much more likely to remain in rural locations or near river transport, even when they adopted steam power. Their raw material costs dictated their location more strongly than the need for an urban labor pool.
The final nail in the coffin for the simple steam equals city narrative must be the data on child labor.
The 1880 census data showed that firms with a high intensity of child labor correlated significantly with rural locations. This further reinforces the idea that the characteristics of the workforce required by the factory were far more deterministic of urban location than the characteristics of the power source.
So the economic reality is clear. Steam power was a necessary tool for the Industrial Revolution, providing scale and flexibility. But it was the organizational revolution, the decision to concentrate labor into the factory system, that provided the sufficient conditions for the massive urbanization spike we associate with the era. The factory system was the turning point.
And if we look past that 19th century urbanization debate, we see this continuous innovation aimed at solving the inherent thermodynamic inefficiency that still plagued even the best reciprocating steam engines, which leads us to the ultimate form of modern power generation.
Even after Watt perfected the separate condenser, there was still heat loss. The steam cooled as it expanded within the cylinder itself, which led to condensation and efficiency loss.
That drove the development of compounding. Pioneered by engineers like Arthur Wolff in the early 1800s, compounding meant expanding the steam not in one large cylinder, but sequentially across multiple cylinders of increasing diameter.
A double expansion or triple expansion engine. It sounds complex to build, but simple in theory. You're just trying to squeeze every last bit of energy out of the steam before you exhaust it.
Precisely. The key gain was dividing the overall temperature drop into smaller steps. This process drastically reduced the temperature swing within any single cylinder, minimizing that wasteful cylinder condensation. It just extracted the maximum practical work from the steam.
And why go through all that effort and complexity?
For certain applications, the efficiency gains were non-negotiable. Compounding became almost universal for marine engines after 1880. For shipping, efficiency was directly tied to profitability and range. Better fuel economy meant a dramatic reduction in the massive weight of coal the ship had to carry.
More room for cargo.
Or increased range, which was critical for global commerce. But the ultimate form of steam power moved away from the reciprocating piston entirely.
The steam turbine revolution.
The need for massive amounts of electric power in the late 19th century demanded something faster and smoother than pistons could provide. They reached mechanical and speed limits. They couldn't turn a generator fast enough without shaking themselves apart.
And Sir Charles Parsons delivered the solution in 1884 with the first practical reaction steam turbine.
The turbine converts the thermal energy of steam directly into smooth rotary motion. Unlike a piston engine that has to stop and reverse on every stroke, the turbine operates continuously and smoothly.
And the scaling was almost instantaneous.
His initial turbine generator was tiny, just 7.5 kilowatts. But within 20 years, his company was building units capable of producing hundreds of thousands of kilowatts for major power stations and for propelling the largest passenger liners and battleships.
The turbine virtually replaced reciprocating engines in large electricity generating stations because of its efficiency, its high speed, and its smooth rotation.
And it's important to realize the contemporary legacy here. Today, the Rankine cycle, powered by steam turbines, generates an astonishing 80 to 90% of global electric power.
Drawing heat from every source imaginable: coal, natural gas, nuclear reactions, concentrated solar. So the ultimate 21st century legacy of Hero's ancient curiosity and Watt's efficiency drive is not the puffing, chuffing piston, but the massive, silent, ultra-high-speed turbine quietly generating the vast majority of our electricity.
But we can't leave the story without acknowledging the dark side of high-pressure steam and the essential role that failure played in creating the standards we rely on today.
The history of steam power is unfortunately peppered with fatal boiler explosions, tragic events that remind us of the immense and volatile power being harnessed.
These disasters were catalysts for change in regulation. Consider the 1838 explosion of the steamboat Moselle on the Ohio River. The captain, trying to win a race, pushed the boilers past their limit. This event killed over 150 people and led directly to the first U.S. federal safety regulation, the Steamboat Act of 1838.
And a later tragedy: the 1905 Grover Shoe Factory explosion in Massachusetts, where a massive boiler failure killed 58 people and leveled the factory.
That tragedy proved that random state inspection wasn't enough. These events drove the engineering profession itself toward rigorous, science-based standardization. This culminated in the formation of the American Society of Mechanical Engineers, ASME, and the establishment of the International Gold Standard, the ASME Boiler and Pressure Vessel Code, first published in 1915.
And that code is still the legal, scientific, and engineering blueprint that ensures the safety of virtually every pressure vessel across the globe, from your home water heater to a nuclear reactor. A quiet legacy born from a very loud and lethal learning curve.
A technological leap always comes with a period of massive risk before institutional control catches up.
We've traced a remarkable 2,000-year history, from a spinning novelty in ancient Alexandria to the economic forces that created modern city, and finally to the massive power grid that defines our global civilization. The story of the steam engine is far longer and its impact far more complex than the simple narrative suggests. The simple narrative says the machine immediately led to massive cities by freeing industry from the rivers. But the robust quantitative analysis forces us to refine that. Steam power was an essential tool, providing the scale and locational freedom.
But the real engine of city growth was the organizational revolution, the shift to the factory system. That concentration of labor increased urbanization almost 3 times more significantly than the mere adoption of steam power did. The steam engine was the necessary hardware. The factory system was the sufficient organizational software.
So what does this all mean for us today? The analysis suggests that large-scale economic activity agglomerates in cities primarily because of the reduction in labor search and matching costs. The technology, the steam engine, allowed the factory to be anywhere, but the organizational need for labor concentration dictated that the factory be in the city.
So if the main contributor to urbanization wasn't the steam engine's power source itself, but the organizational shift and the resulting density of the workforce, it raises an important question for us to consider about our own time. We are constantly crediting modern technologies, ubiquitous high-speed connectivity, AI, cloud computing, with fundamentally altering the world. But are we potentially mistaking the tool for the true catalyst? Is the real driver of social and economic change today simply the organizational structure of the workforce, the way we choose to match talent, aggregate data, or deploy capital that these tools merely facilitate? The technology provides the capacity for change, but organization and culture provide the direction.
A fascinating framework for thinking about future revolutions. It's the operating system, not just the hardware. Thank you for this deep dive.
My pleasure.
And thank you for joining us. We will catch you next time.